Welcome back to another exciting episode of CS250B. This week, this lecture, we get started on the topic of FPGAs, Field Programmable Gate Arrays. You may have heard of this concept already, or you may have not. We are kind of moving into the area of slightly near future technologies now, although some would argue that the future is here already. I mean, yeah, depending on who you ask. So far, we looked at how to better use CPUs, and we looked a little bit in detail about GPUs and how to make good use of them. But those two things were kind of off the shelf. I mean, FPGAs are also off the shelf available hardware as well, but FPGAs give you, we'll get into more details, but it's a fabric on which it lets you customize your hardware to a much greater degree than CPUs and GPUs have. And it's still a not as cleanly defined area as the previous two topics. So that's why I'm calling it slightly near future topics. But it does seem that it will become a here and now topic very soon. So hopefully this will be useful in case you ever find yourself in need of looking into something like this. Okay, now where's my mouse pointer? Ah, here it is. All right. Right. If you remember the presentation on accelerators and where we can actually get the high performance of accelerators, remember there were multiple steps that the paper that we saw was taking, starting from a general purpose processor, the leftmost bar here, all the way to a application-tailored integrated circuit, application-specific integrated circuit, a chip that is tailor-built, bespoke design for this one particular application. And on the way, and remember this is a exponential scale on the left, and on the way from a general-purpose processor, and until we achieve 2 orders of magnitude or more performance, and also similarly with power efficiency, 2 orders of magnitude performance with ASICs, the authors of that paper were trying out various different levels of application specificness. The first step was that they introduced SIMD and vector operations, so kind of like SIMD extensions on CPUs we've seen, and GPUs. And then they did operation fusion, which is creating application-specific instructions, but these instructions still adhere to the RISC instruction format. So 2 register inputs, 1 register output. These things may be doing more complex things like fusing multiplication and addition, but still they took in as input 2 register inputs and emitted 1 register output. But even there, I mean, just getting from SIMD to an operation fusion did give them an order of magnitude better performance, but it was still leaving a lot on the table if we wanted to get to the level of ASICs. So if we wanted to get to the level of ASICs, you don't necessarily have to go all the way, it seems, as long as you are able to add so-called magic instructions, which break away from the restrictions and regularity of these RISCs or even CISC structured ISAs. So these special instructions, these magic instructions, have their own memory. Instead of necessarily communicating with the register files, they have their own memory. They had their own scratchpad memory. They had typically they will take multiple cycles and variable length cycles to complete. Pretty much it was these magic instructions act like coprocessors or even parallel separate processors that the original processor communicates with to send jobs and get pulled when the jobs are done, things like that. So in order to get, I guess this is the good news and the bad news. Good news is that we don't always have to go all the way to ASICs to get this kind of performance, but we do have to at least break away from the regularity of a structured ISA. The instructions themselves have to be drastically tailored to each application in order to get the ASIC level performance. And this is still kind of a good news because ASICs, which are using the silicon budget that we have on these, Moore's law boosted chips, all the silicon that is available for optimized design for this particular application. So as long as we operate on top of this, silicon, Moore's law, transistor-based technologies, ASIC, spinning an ASIC for that particular application is the maximum performance we can get with the realistic technology, underlying fabrication technologies. Given these restrictions, spinning an ASIC for that particular application is the maximum performance we can get. So it's kind of a good news that we can get there without technically, we can get there. So in order to get maximum performance we can from the silicon budget that we are given from a chip, we do need to break away from regularly structured ISAs. We need to have application-specific instructions, separate memory, and interfaces, et cetera, et cetera. The reason I mentioned that we don't have to go all the way to ASICs is kind of a good news, is that spinning an ASIC is an expensive proposition. It takes a long time to design. It takes a lot of effort by highly trained experts to actually pull it off. It takes a lot of money because you have to actually design a chip. You have to simulate it before you actually can, you have to simulate it to death so that when you actually get a request and receive a physical chip, you don't have to take it back to, second rounds of debugging, although most of the times you do eventually have to. But because it will take multiple months of time between the point in which you send out the design to, say, TSMC or other fabrication plants, it will take multiple months of time between when you send out the design to the fabrication plant and you actually get your chip in the mail. If you have to go through multiple rounds of design, that would be a pretty expensive thing to do, both in terms of cost and time. And on top of that, if your chip, and this is, I guess, in many cases, this is true, if your chip has a drastically different interface in terms of which pins do what, your chip isn't going to have the exact same form factor as, say, an x86 processor. It's not going to have the exact same communication interface as an x86 processor. You can't just plug it into a motherboard. So depending on, most of the times you will actually have to build a PCB, a printed circuit board, a tailor-made motherboard as well for talking to your ASIC. And once you have a board that talks to your ASICs, that whole board also has to talk to the rest of the system, either by having a Ethernet port or having a PCIe endpoint, things like that, to either plug it into a host machine or plug it into the network. So all of that incurs engineering cost, and it's not something that someone used to software engineering can kind of jump in overnight. And it will take multiple highly trained professionals in this particular field, and it'll take multiple months to get the design and simulation and everything right. And it'll take multiple months for the implemented ASIC to come back, and it will take potentially months and months to actually debug it to make sure that nothing is out of the ordinary. And the kind of things that can go wrong during a ASIC production cycle is also kind of scary as well. I've seen people have, I won't go into details, but I've seen people who try to spin their own ASIC implementations of general purpose processors, for research. And strange things happen. Like, for example, you may have a silicon die in the center of a plastic packaging, the chip package, and you will have copper wires connecting each of the physical pins on the package to I/O pads on the silicon die. And sometimes when manufacturing processes, there are little glitches in the manufacturing process, and the wires are not completely straight. And you might have crosstalk between these wires, and when you plug it into your machine, you have no idea why this isn't doing anything. So doing an ASIC design is a very involved process. It's a difficult thing to do, unless you're an expert. If you're an expert, as usual, you can do it. And yeah, there are a lot of cost trade-offs to be made when you want to actually get to this level of performance with ASICs. But of course, if it's a common enough application, the photo you see on the left here is a TensorFlow processing unit, TPU v3, built by Google. plugged into their clusters. So this is a machine learning accelerator, both for training and inference. And you can see that they have their purpose-built chips with their water cooling infrastructure. And this whole board, this PCB board, was also designed as a companion to the chips. And this PCB board pins out Ethernet ports, which these boards can use to communicate, to plug into the rest of the system network. And this kind of for this kind of an important application, like neural networks, it makes sense to invest this much time and effort and money and build a lot of them to actually get the performance and the power efficiency, and the benefits do outweigh the costs in this scenario. So that's why some people do it. And we'll actually, later in this course, after we talk about FPGAs, we're going to talk about some neural network accelerators on ASICs to look at what kind of design trade-offs are made in that area. But this lecture, we're not going to talk about this particular topic. But anyways, ASICs can give you superior performance and superior power efficiency, but it does incur a significant engineering and cost and everything to do. Yeah, if we put everything on a slide scale between flexible and easy to program computation fabric and efficient and high performance but difficult to program computation fabric, on this end we will have things like ASICs, which would be super difficult to do, but it does give you absolutely superior local maxima power and performance. On the other end of the spectrum, we can have general purpose CPUs, RISC CPUs, x86s, ARMs, and RISC-Vs, which are very easy to program because you just write C or Python or whatever, and your compiler and interpreter will try to take care of it for you. And in the middle of this scale, we have things like SIMD extensions, which tries to add a little bit more computation density to general purpose processors. But as you probably noticed with the SIMD extension, is trying to use AVX in maybe in relation to Lab 1, you may have noticed it's not as seamless or transparent as the other features in the CPU are. And we also talked about GPUs, which all move much further down the efficiency and performance scale of this slide scale. But they are also a little bit more difficult to program. It forces you to write in a parallelism-aware manner, and it hides less and less features about the underlying computer architecture. So you have to know more about the architecture to get more performance out. And the trade-offs in flexibility and performance is quite stark. This is a chart which compares the performance of these, let's see, yeah, performance and energy efficiency on cryptocurrency mining. I think this was from Bitcoin. And if we look at so left axis is throughput in terms of performance, right axis is power efficiency in terms of performance per power. And this pretty much shows the x-axis shows the progression of time, popularity pretty much. The progression of time part is less important. The important part is these y-axes are, again, exponential scale, logarithmic scale. So as we move from CPUs to GPUs to ASICs, the performance and power efficiency you can get is multiple orders of magnitude higher. This scale is even worse than the chart that we saw in the previous slide with the video processing application, potentially because the computation density of crypto hash mining is even denser, simpler algorithms pretty much. Less memory accesses, more in-depth computation. I could guess if we had built a accelerator for something like the Black-Scholes algorithm that we saw at the end of the graphics lectures, the result might be something similar. So between the trade-offs of GPU and ASICs, it's a pretty big jump. It's a pretty big jump between just going to the store and buying, if you can find, newest top-of-the-line GPUs if they're in stock. Just going to the store and buying a GPU to designing your own transistors, logic, and sending it off to a fabrication plant, designing your own motherboard, that's a pretty big jump. And that's where FPGAs come in the middle. It represents a middle spot in the programmable and performance trade-offs. It has at a very high level, it tries to have the efficient, programmable, dedicated circuit aspects of ASICs, but still packaged within in a relatively easy to program kind of a abstraction. So you can see from this position here, if FPGAs are probably less efficient than ASICs, more efficient than GPUs, but if more difficult to program than GPUs, easier to program than ASICs. And we'll get into details about what exactly FPGAs are and how they're programmed and why it's difficult or easy, etc., in the next couple of slides. And I'm a well-known FPGA fanatic, FPGA aficionado. A lot of my research is organized around FPGAs. I will take any opportunity to get on top of a soapbox to shout about the benefits and superiority of FPGAs. So if you want, you can try to take the following with a grain of salt, but I don't think I think I'm being pretty fair. Anyways, so what are FPGAs? FPGAs, short for Field Programmable Gate Array. Of course, all the words here are active words, but one of the important parts is that it's field programmable, meaning it is you can buy a chip, a blank FPGA chip, and you can reprogram it to be whatever, to work like any ASIC that you want. It can be configured on the fly while it's powered on to be configured to act like any ASIC. Of course, this does come with a little bit of caveats, but we'll talk about this in more detail in a bit. So acting like any ASIC, pretty much meaning, hopefully, it gets near to that power efficiency, the performance of the dedicated ASIC. And it can do many things. Traditionally, FPGAs were usually used for, long time ago, they were usually used for ASIC prototyping in order to try to build your complex design in FPGAs, verify it works before you send. And it was one of the many layers of debugging and verification you had to go through before you actually send off your ASIC design for fabrication. But now it's becoming more and more important as a computation acceleration engine. And the FPGA chips look like this. Left, you see a Xilinx, I think it's a Vertex chip. You see the Intel designed Stratix 10 chip. If you are not familiar with the fact that Intel built stuff like this, there's a little bit of history later as well, which talks about this aspect. So the analogy between CPUs and GPUs and FPGAs is that CPUs and GPUs come with fixed circuits. I mean, this is you get a motherboard, when you buy a computer, you get a motherboard with a CPU or GPU plugged in, and you write software, which is programmed on volatile, DRAM, which the CPU or GPU reads and acts according to their instructions. On the other hand, FPGAs give you analogous to giving you a big bag of components. You can build whatever you want with these chips, as long as it's within the confines of the number of components that are available in the bag. You can build whatever thing you want. It could be GPUs or CPUs, which load and act according to instructions, just like CPUs or GPUs. Or you can do something drastically different, like the TensorFlow processing unit, which it does kind of have a software, but not to the level of general purpose CPUs or GPUs. So you can do whatever you want. You can design a CPU or a GPU, a dedicated processing engine, whatever. So this sounds a little bit too good to be true. Do we actually get all the benefits of ASICs, but do we also get to circumvent the complexities of ASICs completely? So if you compare compare FPGAs to ASICs being application-specific integrated circuit, which are special purpose. I mean, we talked about this multiple times already, but ASICs are special chips which are purposely built for an application. ASIC Bitcoin miners. Intel has this neural network accelerator you plug into to a USB port. The thing with ASICs is that once you expend the effort to design your circuits, to debug your circuits, verify your circuits, and then send it off to production, and then you get your physical chips back. Not only is that a relatively costly process, once you get it back, the functions, the circuits that you design and fabricated on your chips cannot be changed after the fact that you get these chips, physical chips back from the factory. The benefits of FPGAs is that they can be field programmed, meaning once you have the board, once you have the physical chips, its functions, the internal circuits that it internally implements, can be changed completely whenever, while it's powered on. Well, of course, it has to be powered on, but yeah, you can reroute the silicon, you can reroute the circuits, transistors, computation units, ALUs, anything. So that's good. And the way it does it is that we'll get into details of how it does it in a bit, but the FPGA fabric emulates custom circuits on a relatively thin emulation layer, so that it doesn't actually have to change the underlying silicon itself, because that's not possible, but it has a highly configurable programmable units inside the FPGA chip, which can be configured on the fly to act like any other circuitry. The thing is, the downsides of this is that emulated circuits are not as efficient as bare metal, of course. If you compare the performance of the same design circuits running on an FPGA compared to the same design circuit running fabricated on an ASIC, of course, there will be a pretty significant performance and power efficiency differentials. Typically, these numbers are, highly dependent on the applications, highly dependent on what your design looks like. But a rule of thumb is something like you can get 10x or more performance if you actually go all the way to an ASIC, because you can have larger circuits, because the circuit density is higher if you're not emulating something, if you're just using the raw underlying silicon to do something. Also, it lets you use a faster clock. We'll get into details about this in a bit, but typically, if you use a not necessarily top of the line, but if you go all the way to ASICs at this day and age, you typically aim for clock frequencies of 1 gigahertz or above, 1 to maybe 3 gigahertz, if you want to build something in an ASIC. On the other hand, if you buy a pretty decent FPGA on the market right now, go to Amazon and buy one. The clocks, if you do a good enough job in designing an efficient circuit, you can maybe achieve 400, 500 megahertz. So there is a pretty significant clock frequency differential, with why we'll get into it a bit. So there's the issue of 10x performance differentials. There's also 10x power efficiency differential as well, because of the overhead of this emulated emulation layer. But this is still significantly better than general purpose offerings like CPUs and GPUs, which we'll get into in a bit. Well, the comparison of which we'll get into in a bit. And because FPGAs are often sometimes used as stand-ins for ASICs, which can be put into any kind of form factor. You see, there are examples of USB pluggable accelerator cards. The TensorFlow processor we saw in the previous slides, they're just standalone boards that plug into a network, et cetera, et cetera. And in order to take advantage of these various system architectures, where the accelerator can go to be useful in terms of performance, power efficiency, manageability, USBs are easier to manage, et cetera. So FPGAs also do come in many forms. There's multiple different offerings. The most widely available are PCIe attached FPGAs, kind of like GPUs. You plug it into your motherboard and you use it in a similar fashion to GPUs. And this is the form that we'll talk about, I think, most often, at least right now. Other offerings include in storage. There are a couple of companies, including Samsung, which are exploring putting FPGAs in the PCI attached storages themselves. Because if you're doing something like big data, you're going to be streaming data from storage anyways, because oftentimes they're not really cacheable. And if data is coming from storage anyways, it might be useful not to bother the CPU at all and do some computation on the FPGA, on the storage, before the data has to be transferred to the host in the first place. So there's that. Another really popular method that are being explored is in-network, meaning FPGAs are plugged into the network interface, the network interface card. These are called smart NICs often. And smart NICs are becoming pretty much here in the present. Microsoft Azure has, I think at this point, every single Microsoft Azure node has a smart NIC with an FPGA in it. Who else? I mean, there's a couple. There's a lot of research projects. I don't know if that's this new smart NIC offering from VMware has FPGAs or just CPUs. I don't remember at this point, but yes, putting computation in network interfaces themselves are becoming a pretty popular thing to do. And there's another architecture, which is under active pursuit right now, is integrated into the CPUs. For example, Intel is, I think they have prototypes. They really do have, they absolutely do have prototypes. I don't know if they're off the shelf. I don't think they're off the shelf available yet, but there are Xeon processors with integrated FPGAs which communicate over a cache coherent interface between the CPU and the FPGA. And there are also patents and known projects in which Intel and AMD both are aiming to put small pieces of FPGA fabric on the processors themselves and have them communicate either by cache coherent communications like the one you see here, or by kind of like instruction extension sort of an approach, kind of like how the AVX 512, there are mentions about that having provisions for using that 512-bit interface to communicate with custom designed FPGA implementations of custom designed instructions. So a lot of things are being explored right now. This is one of the reasons I mentioned that we're at this point, we're kind of looking into the near future, because a lot of these things are all under active investigation. But the common theme is that they do give us high performance at pretty high power efficiency, which is what brings us to how is it different from CPUs and GPUs. GPUs we've talked about in depth already, which is the other major computation accelerator. And I mentioned already, CPUs and GPU hardware is fixed. The silicon themselves are fixed, which is kind of true for FPGAs as well at a certain abstraction level, but you do try to emulate custom circuitry on the fixed function, already fabricated FPGA circuitry. Anyway, CPUs and GPUs hardwares are fixed. That's why they're called general purpose. You can make them do whatever you want by writing software. Yeah, we write programs, which are sequence of instructions in the form of software for them. FPGA hardware is not fixed. That's why it's called, that's why it's special purpose. The hardware themselves can be whatever you want. Will our hardware also require or support software? It really depends on what you want to do. On the one end of the extreme, you can do something like you can design a RISC-V processor that will be programmed and run on an FPGA, and it will just be a regular old processor. It can act like a processor. But depending on dynamic profiling that you do on the program that this process is running, dynamically you can discover something like, oh, maybe this program will really benefit from this kind of an operation fusion. And merging 2 instructions or 4 instructions together, this program can really benefit from that. And because the circuits programmed onto an FPGA can be dynamically reprogrammed, you can dynamically, maybe not dynamically, but the next time you run this processor, depending on how you designed it, it can also be dynamic, but that goes in going into the weeds a little bit. And the next time you run this program, next time you fire up this processor, you can reprogram the processor to now include these new special instructions. And it takes a couple of seconds to reprogram the FPGA to, depending on the technology, it can take less than a second, but it takes a short amount of time to reprogram the processor inside the FPGA to completely change the implementation of the processor to optimize itself for the particular software it's running. Or on the other end of this extreme, you can just design a dumb engine that will just take as input multiple streams of input and spits out another stream of output, depending on the computation it wants to do. You can do whatever you want, depending on your effort you want to put in, the power efficiency you aim for, the performance you aim for. And optimized hardware implemented on FPGAs is very efficient. The rule of thumb is, and this does come with some asterisks because it really depends on the application. If you're doing matrix-matrix multiplication, oftentimes GPUs are pretty much tailor-built for that kind of application. So FPGAs can sometimes do better, sometimes do worse, depending on who you ask. If it's a very irregular kind of application, if you're doing shortest paths on graphs for example, if you're doing bit twiddling because you're doing cryptographic hashing or something like that, FPGAs, similarly positioned FPGAs typically better in terms of power. But the real benefit of FPGAs comes from the better power efficiency, typically an order of magnitude power efficiency. The similarly positions FPGAs and GPUs typically do come at a significant power efficiency differential. So this sounds, so far all of this sounds very good. The downside is maybe, so to speak, when we compare the multiple characteristics of GPUs and FPGAs, is that if we look at features like portability, performance, flexibility, all that stuff, while GPUs and FPGAs do come at kind of similar performance, FPGAs do have better power efficiency most of the time, but it also comes at a significantly steeper curve in terms of, design efforts. So again, it becomes like everything else. It is another point in the trade-off scale between programmability and performance and power efficiency. So if you're willing to put in more effort, or if your application is more critical in terms of performance and power efficiency, then it might benefit to put in more effort into spinning something on an FPGA. And it becomes, this is another area that is under active investigation right now, especially in my group, is if we go to power constrained deployments like edge devices or even IoT nodes. And when you have a stringent fixed power budget, sometimes you do really have to put in this effort if there is some algorithm that you really have to run on an edge node, because otherwise, for some reason, for example, because otherwise the transferring data over the wireless network is going to eat into your power budget anyways, and there could be multiple reasons. Anyways, so these are the high-level characteristics of FPGAs. And how we use FPGAs also, it depends on the architecture and the positioning of the FPGA. But if we just look at the PCIe attached accelerator that we looked at in the previous slide, the use of an FPGA accelerator is kind of similar to what we did with GPUs as well. We have the CPU, we have the FPGA, time moving forward. And if there's data we want to process, we then copy it over PCIe to the FPGA. And on the FPGA side, you can really do whatever you want, but oftentimes what a power efficient and high performance thing to do is that you can design something like a stateless accelerator, dumb engines that just do computation when data is available. As if data comes in, if the engine notices that there's data coming in on this side, it does a lot of computation. It could be floating point, mathematics, whatever, and then spits out the answer at the other end, which gets then copied back to the host. No instructions, no nothing. I've heard some people describe this as a processor with a single instruction, which is called every time new data comes in. Every time new data comes in, implicitly that single instruction in the ISA is executed, which does a lot of computation. It could be, I don't know, calculate the gravitational pull of between two particles. It could be trying to align a short-read genome sequence to a reference genome, whatever. But all of that high-level functionality described into a single instruction. So just say, execute that instruction. Every time new data comes in, the engine does a lot of stuff. It could be talking to DRAM on the board, etc. And at the end, it spits out some data, which gets copied back into the host. So this is, I think, for popular PCIe attached FPGAs, this is typically what the usage will look like. It can be streamy, so you can be sending data while data is coming back, so on and so on. I mean, because the engine can be, the semantics of the engine can be whatever you want. It can act like normal, not normal, but it can act like basic GPU kernel execution models as well. You can copy a bunch of data over to DRAM. You can invoke the kernel, and when it's done, you can copy the data back in a blocking fashion. You can do that as well. You can do a streaming, fine-grained streaming as well. Reality can do whatever you want. And a lot of the benefits of FPGAs come from multiple sources, including including fine-grained parallelism of having special purpose circuits. And this is one of the big benefits of ASICs as well, not just FPGAs, but because in this characteristics, FPGAs and ASICs share a lot of characteristics. So yeah. Example, we can use the example of calculating gravitational force between two particles on a two-dimensional plane. So gravitational force calculation is, high school stuff. You calculate the distance, squared distance between these two particles, x1 minus x2, y1 minus y2, squared and summed. And you use that to divide the multiplication of mass multiplied by the gravitational constant. Because this operation uses 8 mathematical operations, square, subtraction, multiplication, division, multiplication, and multiplication. So 8 floating point instructions. If you run it on a general purpose processor, it will take 8 cycles. And there are asterisks here because it really depends on whether you have things like superscalar, out of order, if you have SIMD, et cetera, all these numbers can change. But the bottom line is that if you have one ALU in your processor, it's going to take 8 cycles, 8 clock cycles to run this computation on that over multiplex this equation over that one ALU. If you have multiple ALUs, then great. Special purpose units, like what you can build on FPGAs or ASICs, can spawn many ALUs for parallelism, as many ALUs as you want. So if you really care about performance, what you typically would do is that you would spawn 8 ALUs for these 8 computations, and depending on your on the timing characteristics you want to read, you can build a tree that looks like this on the left. So it'll take 1, 2, 3, 4 clock cycles, depending on the breakdown of the dependencies. But the bottom line, it will take 4 cycles of latency, but because it will be pipelined completely. If you remember, the pipelining aspect of the was described in undergrad computer architecture. These 4 stages will be completely pipelined, meaning even though the latency of this operation is 4 cycles, you can always get one answer out every cycle as long as you enqueue all these parameters, a set of all these parameters at every cycle, G, M1, M2, X1, X2, et cetera, et cetera. So the throughput is always maximum. Latency might be 4 cycles, but the bottom line is that because it's pipeline, all these ALUs, 1, 2, 3, 4, 5, 6, 7, 8 ALUs are always doing some work. So in terms of flops, floating point operations per second, compared to a single thread software, which is multiplexing 1 ALU, which the performance of which will peak at 1 flop, 1 floating point operations per cycle, because we have 1 ALUs. this design can be running 8 ALUs at any given time as long as there's data to process, giving us 8 flops per cycle, which is much better performance. Of course, general purpose processors try to catch up to this by using SIMD and superscalar and things like that. But for very complex instructions, operations, this is exploiting fine-grained parallelism in this way does give you a very big performance boost. And of course, if you either care about latency, or if the ALU, and we'll talk about propagation delays and timing characteristics in a bit, because unfortunately that's a very important part of FPGA design and circuit design. But if these individual ALU operations are lightweight enough that the latency internal to these things are short enough, then maybe we can merge these things together inside a single clock cycle so that we can do more operations per cycle. This can give us lower latency, potentially lower chip resource utilization as well, because we don't have to have pipeline registers between these more pipeline stages. And if the clock is slow enough, or if the ALU is efficient enough, then we can even have everything done in a combinational circuit within a single cycle. Of course, this may slow down the clock. If we're talking about floating point operations, most of the times, every single floating point operations has a multiple cycles of latency. So in reality, the pipeline depth will be much, much longer. Most likely, a design like the one you see on the left here will be still completely pipeline, but with a latency of, say, 4 dozen cycles of latency. But it will be completely pipeline. Every cycle you can enqueue new data, new requests, and every cycle you will get an answer out. And the flops throughput will be extremely high compared to a general purpose processor. And not only this, not only are we getting higher throughput per cycle, this approach also uses much less. I mean, this approach is often much more efficient, because this chart shows power efficiency comparisons. But in terms of silicon usage, this is pretty analogous as well, because things like the fetch decode unit, instruction cache, register file, these things are no longer required. If your accelerator design is tailored to your application, it doesn't have an ISA to speak of, it doesn't require fetch or decode units and things like that. So so what happens is that not only is an instance of the gravitational force calculation accelerator that we saw in the previous slide, not only is the throughput of that new design be potentially higher. I mean, of course, there's some trade-offs because the clock speed will be lower on an FPGA. On an ASIC, the clock speed will not be lower, so that you get even more performance. But on an ASIC, because the clock speed is lower, you with a single pipeline of that accelerator module, you probably can get higher performance because of the higher latencies and pipeline floating point operators and things like that. You probably will still get higher performance, but at the same time, you get much lower power consumption. You also get much less chip resource utilization as well. You use much fewer number of transistors to actually pull off that similar or higher performance computation. And a result of that, better resource utilization, is that you can take advantage of more coarse-grained parallelism as well. So units of coarse-grained, coarse-grained. Units of coarse-grained parallelism for general purpose processing units are threads, which are kind of coarse. I say kind of coarse because there are things like hyperthreads and things like that as well. But parallelism comes from more cores, pretty much. And special purpose processing units, like the pipeline implementation we saw before just now, can also be replicated for parallelism. And the thing is, if you have large and complex accelerator modules, maybe few of them can fit on a chip. If you have very small, very simple processing units, then many can fit on a chip. A very simple accelerator, I mean, in the context of accelerators, the pipeline implementation of the gravitational force calculator that we saw in a couple of slides back is a very, very small, very, very simple processing unit. And even though a single pipeline, let's for the sake of argument, if we say that a single pipeline of that accelerator unit has a similar performance to a processor thread. On a modern FPGA board, ultra-scale series chips, and we'll get into what those are in a bit, or even a 7 series chip from Xilinx, we can probably fit maybe not hundreds, but multiple dozens of those things on a single chip, which is much larger in terms of numbers and also in terms of resulting performance compared to what a general purpose multi-core processor can do. And that's where a big portion of this performance improvement comes from. And because the power efficiency per ALU is also very high for FPGAs, so that's where also power efficiency also comes from. And yes, we mentioned this point multiple times already, but all of this comes from the fact that we only generate hardware which is useful for the application that we're trying to run. If we don't need instructions, we don't need to do decoding. If we don't need to do caches, we don't have to have caches. If the communication, we know the communication pattern between these multiple pipelines beforehand, or if we know that there is no communication between these multiple pipelines, we can either have very efficient implementations of coherence between these cores, or we can afford to not have coherence at all. So all these simplifying factors, simplifying in terms of the microarchitecture, not necessarily your design efforts, but all these simplifying factors do result in much higher performance, much lower power consumption, much lower chip resource utilization per core, meaning we can stamp out larger number of these things on available FPGA chip resources, which results in significantly potentially multiple orders of magnitude higher performance compared to general purpose units at a order of magnitude better power efficiency. So that's where all these benefits come from. So that's my soapbox. And these are all very good benefits. But of course, it can't all be benefits because we do know that it does sit on the less programmable side of the power programmability efficiency trade-off. So, and that's where the hurdle of using FPGAs come from. And because I am on a soapbox, I will even take this chance to say that because the hurdle is programmability, if there is a person who can program these things, and it is a very valuable thing to have, because you can get this kind of improvements if you know how to do it. Anyways, the hurdles of FPGA programming, there's a couple, there's actually quite a few of them, but the most prominent of which is that it's very close to actually designing a chip with not all, but most associated difficulties. You don't have to design PCB, for example. When you buy an FPGA peripheral, it will come with a nicely designed board, which kind of is proven to work. So there's a lot of things you don't have to do, but still internally to the chip, a lot of the expertise you need to actually deal with FPGAs at this point do share a lot of characteristics with actually designing a chip. So if you are adept at doing FPGA design, I've been told it's much easier to actually jump into proper ASIC design as well. And I've seen a lot of colleagues who actually kind of jumped the shark, ended up designing their own ASICs for research and other purposes as well. So there's that. And these caveats include things like topics including signal propagation delay, clock speed, managing those. If you took my undergrad computer architecture course, I talk about that quite a bit. There's also trying to do circuit design, which results in acceptable propagation delay, because otherwise you'll get a slower clock. You also have to do explicit pipeline designing for performance. It kind of turns into doing computer architecture design, designing your own processor, things like that. Also, you have to be mindful and wary and do resource management of on-chip resources, things like available transistors on a chip, managing SRAM capacity on a chip, things like that. We'll get into each of these things in a bit because I'm taking this chance to spread the gospel of FPGAs and FPGA expertise, and hopefully it will be useful for everyone at some point. High-level tools do exist, which tries to hide all these characteristics, which tries to hide the existence and importance of clocks and propagation delays and resource utilization and pipelining and things like that. There are high-level tools that tries to hide this. But unfortunately, most of them are not very effective right now. There are approaches, including using OpenCL, trying to compile OpenCL code to actual silicon. There are approaches which tries to extract parallelism, fine-grained parallelism from any random C code, and then tries to turn that into a circuit. But we'll talk about this in a bit more detail later. But all of these even often represent a trade-off between ease of programming and performance/utilization. So if you're unlucky and if your application isn't a good fit for the optimization methods that these tools use, and the unfortunate part is that you can't really predict if this will be a good fit or not unless you kind of know the architecture. And maybe if you know the architecture, you might as well use more efficient lower level languages. But if you're unlucky and if it's a bad match to these optimization tools, then the performance and power efficiency you can get from an FPGA might dip below GPU levels, which kind of defeats the purpose of having FPGAs. And this is not to say that this won't become better. It's not to say that in a year or so, OpenCL code can be seamlessly, efficiently translated to efficient FPGA pipelines. But for the past couple of years, every time I checked, it was still a little bit of distance away. The bottom line is that FPGAs is a prominent technology for performance scaling beyond the end of performance scaling of general purpose computation units. CPUs and GPUs will eventually hit a wall. FPGAs will also eventually hit a wall, just like how it was mentioned in the one of the third paper in the Accelerator lecture we had a couple of weeks ago. If Moore's law ends, FPGAs will also hit a wall, but a little bit of time after the general purpose units hit a wall. So this is one of the most prominent technologies for continued performance scaling once Moore's law ends, once general purpose computation performance scaling ends. That's why a lot of these companies really care about this as a future. FPGAs are represent an efficient use of the increasing transistor budget because it is a platform for specialized hardware. And unlike ASICs, which can, if you put in enough effort, it can give you more performance and efficiency. Unlike ASICs, FPGAs are reconfigurable based on the application or algorithmic changes. And an analogy is that it's kind of like software running on a hardware processor. Sometimes people call the programmable specifications for FPGAs, which you use to program these FPGA chips. Sometimes people call it gateware as a middle ground between hardware and software. So you kind of can think of it like programming a hardware chip to act like different pieces of hardware. And of course, a single FPGA hardware can also be shared between different applications, shared between different users and applications and use cases, depending on which combination of accelerators you program onto it. So that's also a benefit as well. Another benefit which FPGAs exploit to get performance and high efficiency is that common operations, not high-level accelerators, but common sub-operations are often also embedded into the FPGAs using ASIC blocks, little blocks of custom designed operations in the form of ASICs. Because these things can give you high performance, low power, and small size. And these ASIC blocks include examples like arithmetic units, ALUs, shifters, neural network operations, high-speed communication links, et cetera, so that you don't have to use the reconfigurable resources on the FPGA. And these dedicated ASIC blocks also, because they are ASIC blocks and not reconfigurable blocks, also run at a much more compact form factor, also run at a much higher clock frequency, multiple gigahertz. So it looks a kind of bit like this. On a general purpose CPU, the ALU, which does the actual data path work, you have a small number of them. There's a lot of surrounding infrastructure for managing caches, fetch and decode, things like that. For GPUs, the relative size of these management units as compared to ALUs are much smaller. So given a similar level of transistor budget compared to modern CPUs and modern GPUs, they can afford to have much more ALUs per total silicon budget because the surrounding infrastructure is much, much more smaller. FPGAs take it much further so that most of the chip can be used for actually implementing ALUs. And because we stopped trying to be general purpose, instead we would aim to support general purposeness by reprogramming the FPGA if the application changes. That's how we try to get general purpose, not by having a single design of silicon be general purpose in and of itself. So FPGAs tries to get, the goal at least, is to get more ALUs on the same chip resources, doing more computation, more useful computation, and have much less surrounding infrastructure taking care of all of this. So given the same transistor budget, FPGAs, and of course later ASICs as well, is a way to get more efficient utilization of these resources. So that's why it's a prominent technology for performance scaling beyond general purpose processor performance scaling kind of ending. Instruction level parallelism scaling has kind of ended, et cetera, but custom designing circuits can still exploit much, much more finer grained parallelism from the application that you're running. And this is one of the reasons that prominent chip designers have been jumping into the FPGA space. And back in 2015, this was a really big news at the time. Intel acquired Altera, which used to be the #2 FPGA designer and manufacturer in the industry, for $16.7 billion, which it is still the largest acquisition in Intel history, which is kind of cool. And just now, right now, AMD is acquiring Xilinx, which is the largest player in the FPGA industry right now, valued at $35 billion. So this is a pretty, I guess, so to speak, this is kind of the writing on the wall. It's going to be an important piece of technology in the near future. And if you look at other user case industry examples, Amazon has in their AWS cloud offerings, they also have nodes with FPGAs installed on them called the F1 nodes. I mentioned this already, Microsoft Azure, each of their nodes have an FPGA plugged into them in the form of a smart NIC, which is also kind of interesting. And there, a lot of the applications, a lot of the operations that are run in the Azure cloud, for example, indexing for Bing, something like that, a lot of them are offloaded onto the FPGA as well. And compared to the ASIC approach of Google with the TPU, comparing that to the FPGA approach of Microsoft is kind of interesting, because Microsoft at least claims that they are able to get ASIC levels or even higher levels of performance and power efficiency by optimizing the underlying computation fabric and dynamically reconfiguring it for the individual models that they're running and things like that. For example, because when the TPU is first designed, at least according to Microsoft, when the TPU is designed and fabricated and the functionality is fixed, you may have, I don't know, 8-bit floating point operators, a bunch of them, 16-bit floating point operators, a bunch of them, but in a fixed budget. As opposed to if Microsoft wants to do it, do something similar, and they trained the model and discovered, oh, this model works better with a specifically structured 8-bit floating point format, then instead of leaving some resources idle, the so-called Microsoft Brainwave platform can be reconfigured on the fly to use the available FPGA chip resources, the silicon resources, to spawn those specific number of specific 8-bit floating point operators, which Microsoft claims is a efficient trade-off and performance. So that's one voice from the soapbox, I guess. Unfortunately, learning curve is still quite high. And that's for the remainder of the FPGA portion of this course. This is what we're going to be talking about the most. And that will be what Lab 2 is based on. We will try to accelerate a neural network operation. It's kind of like similar to what we did with Lab 1 on an FPGA fabric to see the performance improvements, to see the power efficiency benefits that we can get. And in order to get there, we have to, as usual, as we did with CPUs, as we did with GPUs, we have to talk about a little bit of how the underlying architecture of FPGAs actually work and look like in order to reason about how to build efficient software, efficient gateware, efficient architectures on them. And the goal of the FPGA architectures is that to have a single physical chip, which you can just buy from a store, which has been fabricated from a fab plant, from a factory. You take a single physical chip, and the goal is that you want to be able to reconfigure that physical chip to act like any different circuit. The thing is, transistors within an integrated circuit are fixed during fabrication. You can't rewire transistors on the silicon themselves once you actually manufacture a chip. The question is, how can FPGAs actually change themselves? And that's where the interesting architecture of the FPGAs do come in. The basic architecture of an FPGA chip looks a little bit like this, what you see on the left. This is a chip. There's I/O blocks, which represent, I/O pads, which represent physical pins that you can actually use to plug into the motherboard, et cetera, et cetera. And inside the chip, there's a grid of what is called configurable logic blocks, CLBs. Configurable logic blocks, and there is a programmable interconnect, a grid of programmable interconnect, which can move bits between these individual blocks. And these networks are not anything like packet switch networks or anything like that. There's no router in the middle or anything like that. When you program the FPGA, these are circuit switched so that some cables are connected to the others in a physical fashion, so that every single communication can be made to go from one block to the other within that same cycle in a combinational way. We won't go into too much details about the interconnect, except that it is there. It can act like any communication between not any, but that's not our job to worry about. But it can connect pairs of CLBs as a combinational wire. And these CLBs are the ones that are programmable. If you look in the right here, this is an internals of a generic CLB. If you look at the actual CLBs or slice LUTs or slice Ms and all these other names that these different companies call them, they're much, much more complex. But at a high level, at a very generic level, a CLB looks a little bit like this. You have a flip-flop, which can store a bit of data across clock cycles. You have a multiplexer. You have a latch, which all these green blocks are part of the programmable logic. The key part is the lookup table, which can be programmed to act like any logic gate, pretty much. if you want to program a CLB to act like an AND gate, you can program the lookup table to store the truth table for the AND gate. If you have two zeros, you get a 0. If you have two ones, you get a 1, things like that. And because these lookup tables are typically have more inputs than 2, you can use this to program slightly more complex combinational circuits as well. And this is part of the program. A C of these lookup tables is an important part of the so-called bit file, which is what you use to program the FPGA. And so this is programmable. And because you sometimes want to program sequential circuits, which hold state across clock boundaries, you also have a flip-flop, which can store the output of this lookup table from this particular clock frequency. And you can also program, the part of the program is the value of this latch, which basically programs this CLB to directly forward the output of the lookup table or forward the output of the lookup table from the one cycle before. So this lookup table represents the sequential aspect of the circuit that's being implemented. And this latch represents whether this is part of a combinational or a sequential circuit. So by programming these things and also the interconnect network, you can, if you want, you can do something like this. You can program the truth table of this particular CLB to act like an AND gate. And you can program the interconnect to take as input signals from these IO pads and then stream it out into another IO block. So if you do this, if you just did what is shown in this slide, you will take the whole FPGA and then program it such that it acts as a single AND gate. If you, by programming this latch, you can also make it a sequential AND gate as well. So at a base level, this is how it works. And of course, you can program a lot of these things and connect them together using wires, et cetera, to try to implement whatever combinational sequential accelerator module that you want. So at the very base level, this is what the FPGA is pretty much internally. So this is how they actually prototype. This is how they actually map any free-form silicon circuit to the FPGA emulation fabric by using the lookup table. The thing is, and at this point, this is already quite functional. But the thing is, each CLB, at least at a generic level, each CLB acts as a single gate or multiple gates if you can program the 6-input or more inputs lookup tables efficiently. And if you want to implement high-level logic, you might need quite a few of them. And because there are some common operations like arithmetic logic, addition, multiplication, division, things like that, which would be kind of resource intensive in terms of number of gates to implement, and they're used quite often enough that most of FPGAs, even like really cheap ones, $5 ones that you can buy, will have a couple of what is called DSP blocks on the FPGA fabric, which implement a ALU, a very, very simple slice of the ALU that you have to build some management logic around this to actually build a functional ALU. All this thing has is pretty much just a multiplier and a addition core. And it is the surrounding infrastructure's job, surrounding CLB's jobs to make it actually act like an ALU. But instead of having to build, expend transistor resources to build these arithmetic operations, you can use these things. ASIC implementation, little blocks, little shards of ASIC implementation of important functionality. These things are usually called digital signal processing blocks, DSP blocks, because in the olden days, DSPs were what these things were typically used for. Now, maybe some people want to call them neural network blocks. But anyways, each block typically provides an adder and a multiplier, and you can construct logic around it to build any sub-slice of an arithmetic operation that you want, achieving high performance and low resource utilization. Another case of the special purpose blocks include things like block RAM, another row of these things you see here. These things come in because CLBs, while CLBs can act as flip-flops, and depending on the CLB design or depending on how it's organized, if it has, sometimes it even has more resources than just a single flip-flop. But the bottom line is that each flip-flop can store, if you want it to act as sequential circuit components, each flip-flop can store maybe a handful of bits across the clock boundaries. And this is tiny if you want to use these things to build something like a cache memory. You will have to use a lot of these blocks just to implement a few kilobytes worth of memory. And that's if you want to build a design that has a lot of scratchpad memory or caches or things like that, or large FIFOs queues, then this would be an inefficient use of resources. So oftentimes there are some on-chip SRAM resources provided as these special purpose blocks as well. And that's why these are called block RAM. And they're typically in the orders of kilobits per block. And per chip, you would get an aggregate capacity of multiple megabytes. It could be in the orders of 4 or 5, or in newer chips, tens of megabytes of block RAM. So in a similar orders of scale as CPU caches, because they're pretty much the same technology. The interesting thing about block RAM is that because these are, instead of having one or two monolithic memory resources, all these block RAMs are very, very tiny shards, 18, 16, 36 kilobit shards, hundreds of them adding up to multiple megabytes. If your surrounding circuitry uses all of these things independently in parallel, then you can use each of these things to read and write a word of data per cycle, adding up to multi-terabytes of bandwidth in aggregate bandwidth if you're using all of them in a separate high-performance manner. And that's where a lot, and we'll get into more details about this when we actually get to the neural network portion of the ASIC design topics. But because a lot of applications are typically are often, and we've seen this already, a lot of applications are memory bound. This is one of the big things that gives FPGAs the edge, because they can afford to provide memory in very, very small shard units instead of having a cache coherence or banks per core and things like that. This is if we just talk about the efficiency of bandwidth, this is a much more efficient way to organize memory. And on top of this, so these things are the typical resources that are available on normal FPGAs. And on top of this, depending on the deployment target of each of these FPGAs, there are other functionalities that are also provided as ASIC shards as well. These things are efficient because they're ASICs, efficient non-configurable blocks, which are sometimes called hard cores, as opposed to soft cores, which can be dynamically reconfigured, because these are cores that are fabricated onto the FPGA silicon when you buy them, so you can't really change them. Which are called hard cores. Examples of these things include, sometimes they have multi-core ARM cores included on them. For example, if you buy what is called the Zinc series or MPSoC series from Xilinx, you will have 1, 2, 4 or more ARM cores embedded onto your FPGA. So you can boot Linux off them and make them communicate with the FPGA and over generic interfaces and things like that. They also often include something called multi-gigabit transceivers, which are serializing and deserializers for sending very high frequency, multiple gigahertz signals over a pair of wires or things like that. And this is what is used as the basis for implementing the physical layers of many communication technologies, including PCIe, Ethernet, and stuff like that. Also, there's sometimes the physical layer implementations for PCIe or Ethernet, 10 gigabit, 40 gigabit, 100 gigabit Ethernet is sometimes provided as ASIC cores as well, because reinventing the wheel every time is difficult. And also memory controllers, etc. If some FPGA boards come with high bandwidth memory, HBM2, some come with DDR4, some SDRAM, DDR3, LPDDR. There's a lot of offerings, and because reinventing the wheel for every time for memory interfaces is annoying, a lot of times memory controllers also are provided in the form of hard cores. So this is what the internals of a normal FPGA would look like. And we try to make use of all these resources by writing programs that configure all these programmable CLBs to implement any functionality that we want. And when we plug another benefit of buying an off-the-shelf FPGA as opposed to something like an ASIC, trying to spin your own ASIC, is that the surrounding infrastructure in terms of PCBs, wiring, memory, and things like that there are offerings for those things that are available already. An example accelerator card architecture, and if your accelerator is something that you plug into a PCIe port, looks a bit like this. You have a big card, looks almost exactly like a GPU, which plugs into the PCIe, talks to the PCIe. And you have onboard DRAM, which communicates with the embedded memory controller. There's also, you can have things like 1 gigabit Ethernet, 40 gigabit Ethernet, 100 gigabit Ethernet, depending on the board that you buy. And if you want to connect this to your generic custom built PCBs as well, they also pin out some general purpose IO pins and multi-gigabit transceiver pins to plug in expansion cards. This is one example. There are multiple examples. FMC, FPGA mezzanine card expansion, which is one of the standard expansion form factors for companies that build expansion cards for network ports, memory, storage, PCIe, root complexes, and things like that. So this is pretty expandable as well. Sometimes FPGAs can communicate directly to other FPGAs over these FMC communications. And that's actually an interesting project that my group is working on right now. Examples of these kind of accelerator cards include things like examples aren't important, but if you buy one, it can look kind of bit like this. This is an example from Xilinx, soon to be AMD. This is an example from Intel, formerly Altera. And this is an example from Xilinx. And this particular board is something that Xilinx is pushing pretty hard to be the neural network accelerator board. So that's also kind of cool.